morning. The microphone on? Yeah? Okay. I hope you had a nice Thanksgiving. It's our last week. We have 3 more lectures, and then next week is the so-called RRR week. We're hoping to have a number of review sessions and office hours that week, which we'll post soon. I'm here today and Wednesday. I'm out of town on Friday. I apologize for that, but I just wanted to let you know. I do have office hours today and Wednesday, and I hope to be reviewing Unit 4 with those of you who are interested. So today we're going to talk about Technicolor atoms, and this is a case where you've seen some of this, where you've seen flame tests, some of you in high school, where you get certain colors of light emitted. And that's what we want to talk about today. And the first thing that I want to point out for you is this notion of line spectra. What I mean by that is simply that it's not a lot of wavelengths, not a broad distribution of wavelengths that are in the spectrum, but very, very narrow wavelengths. So all this means is that it's very narrow. Okay? I also want to point out that today we're talking about atoms. Next time we'll talk about molecules, and I want you to keep track that these will give different spectra. So next time is molecules, and we've already discussed black body. And these, you want to keep these distinct, because what you're going to find today is that atoms interact with light in a very discrete way. Just very specific wavelengths are absorbed and emitted of light. Whereas for black body radiation, we saw a broad emission of light. And for molecules, we're going to see that it's also broader. So the most important thing here is that these are broad and this is discrete. So those 2 words are important in this. Okay, so the other thing that I want to point out, so that you also keep track of, might be good for you to start to organize for yourself these different ideas and how they connect with one another. We have already removed electrons from atoms, all right? And when did we do that? We did that with the photoelectron spectroscopy. And the main point that I want to make here is that if the energy of the light is greater than or equal to the ionization energy, you can put any energy in. And what happens, the photon comes in, it ejects the electron, and what else does the electron then have once it's separated from the atom? Kinetic energy, all right? But what we're going to talk about today is not removing, but relocating the electron on an atom. And what we're going to find is that this is where we have only specific energies are allowed. So only specific energies, and this is where this word discrete comes in, or quantized. It's only specific energies that are allowed. And the other thing that you're going to have to keep track of is that we're always talking about some kind of energy exchange. And in the last unit, we talked about when a system rearranged from one situation to another, that you could transfer heat, you could transfer work, you could transfer electrical energy. Now we're adding light to that. So what you're going to see today is that we're going to talk about heat, light, and electricity we're going to use as well. So in other words, we are transferring energy by heating things up. We'll put it in as heat, we could put it in as light, we could put it in as electrical energy or electricity. And likewise, we can get it out as all of those 3 things. So you kind of have to keep track of what we're putting in and what we're getting out. This is always about converting one form of energy to another. All right, questions on that? That's just kind of an overview. Okay. All right. So we have revised the models of the atom. We did that last time in particular with this quantum or cloud model of the atom. And right now we have different pictures that we're using. This one shows the energy, and this is just an example where we have an energy scale, and the 1s, the 2s, the 2p, they're all at different energies. And as you go up in quantum number, the energy gets higher and higher or less negative. So the most stable place for the electron to be is where? It's down low, right? In the 1s. This kind of model is one that specifies distance or radius. And this is still kind of a shell model with subshells. And we realized with the photoelectron spectrum that there were subshells. And then finally, this quantum model really helps us understand space. Where are the electrons most likely to be found? All of these models are useful. It depends on the experiment that you're doing as to which one will be the most important one for you. All right, so we're going to start with an experiment. I'm going to do it as a simulation. I want to show you a simulation where we're going to take a look at electrons in, or electricity in, and watch what happens to atoms. And so on this website, this PHET website, P-H-E-T, there is this model that has what's called a discharge tube. So let me explain what I have here. I have an atom that's a single atom, a hydrogen atom actually, that's sitting in the middle of two electrodes. And so what I'm going to do with this battery is I have a potential. I have one side positive and one side negative. And what you're going to see is electrons are going to move across. They're going to go from one side to the other. So they're going to get ejected from the side that's more negative and get attracted to the side that's more positive. So those electrons are going to move across. And what you're going to see, there's those moving electrons. They're carrying energy with them. And those electrons can hit the electrons that are in the hydrogen atom and relocate them. All right, so let me start by just letting the electrons flow across. So they're flowing across with a certain energy. And what you notice is that absolutely nothing is happening. And why might that be the case? Not enough energy, okay? And if you look over on the side at the energy level diagram, you see that the electron on hydrogen is sitting in that lowest energy, most negative state. We know what this value is from photoelectron spectroscopy. And this is the energy at the collision. And you can see that the electron can't just be sitting there. It can't sit at that energy. So what do I need to do? I need to raise the energy up so that the electron can go all the way up to 2. So I'm going to do that by moving the battery. So the energy, you see it's going up. And now, what do you see happening? All right. So what happens to the electron that's moving across that collides? What happens to some of them? When it comes out the other side, what is happening? It's moving quite fast, and then sometimes it moves to the other side a little bit slower. And then what are the little fuzzy things that are coming out? That's light energy coming out. So what you're seeing here is these electrons are moving across. They're transferring their kinetic energy, some of it. Then they move slower, and out comes that energy transfer causes the electron first to do what? To go up to 2, and then what does it do? Comes back down. And when it comes back down, how does it transfer the energy? So in other words, the kinetic energy of the moving electron has pushed this electron up. That moving electron moves slower after that because it's transferred some of its energy. And then this atom is now, quote, in an excited state, hence the song today. It's in an excited state. And as it goes back down, how does it give its energy back out again? As light. All right, does that make sense? So what's going to happen now if I move, if I make the energy go even higher? What do you expect to see? So I'm going to move it up even higher. I'm going to move it way up. Okay, so every so often, what are you seeing now? Every so often, do you see a different color coming out of light? And what's that coming from? So what are all the possibilities here? So notice that sometimes this electron goes up to 2, and sometimes it goes up to 3, and sometimes it goes up even higher. And when it comes back down again, what are all the possible ways that it can go back down? If let's say it's up in 3, where can it go? 3 to 2. And what color comes out when it goes from 3 to 2? Red. And what color comes out when it goes from 4 to 3, I think is probably where we're seeing the blue coming out, right? All right, so the point is that in this case, the traveling electron is giving up some energy, the electron gets pushed up, and then as it comes back down, it emits light. It can also emit heat, it can also transfer the energy as heat. It does it both ways, but we see the light coming out. Okay, questions on that? All right, so let me just return to the slide here. And I think the main thing that I want to just draw for you before we actually take a look is this is an energy level diagram. This is for hydrogen. This is an H atom. And this lowest energy level is called N equals 1. Then there's one up here, N equals 2. What do you notice as we go up in number? They get closer and closer together. Okay, and somewhere up here is the 0. And what does the 0 mean? Ionized, right? That means that this electron down here, up to the 0, means it's ionized. Okay, so we have this traveling electron that comes in with a certain kinetic energy. So this has a high kinetic energy. It goes in, and what happens to this electron down here? It moves up, right? And so as this comes in, what you see is this electron will move up to a higher level of energy. And what happens to the outgoing, that electron that's been moving, that moved in and out? It goes out with a lower kinetic energy. Okay? And then how does this, once this electron has gone up to here, what happens then? Goes back down, and what comes out? Okay, so this is light coming out. So H nu is for the energy of the light. Okay? And if I do it, what are some of my other possibilities? Let me draw it again for you. So what happens if I put it up in, if the energy is enough to put it up in N equals 4? How many, let's say the electron gets up to there. How many different wavelengths of light can come out? Not all, can't be any old wavelength. What are the wavelengths that can come out? N equals 4 to where? To 3. N equals 4 to where else? To 2. N equals 4 to 1. But what about, where else could it go from N equals 3? To N equals 2, to N equals 1, and then this one. So you would see how many different wavelengths of light come out? 6. Okay, so what we're going to do now is actually try that experiment. These are so-called discharge tubes. That's what I showed you. These are lamps that are actually around that you see. You see them in neon signs. These discharge tubes have exactly what I showed, some kind of a high voltage. I used a battery in the simulation. What does that mean? It means that there's a potential difference between the electrons. So we've got electron at a high potential and a low potential on the other side. So these electrons travel through the outer circuit, and then we have a gas that's in this tube. And the one I showed you had hydrogen in there. I had a single hydrogen atom as the electrons went through. So these electrons are passing through here, and we've got hydrogen atoms in this gas, or some kind of hydrogen is one example. All right, so now I have hydrogen lamp, a helium lamp, a neon lamp, and a mercury lamp. And what you're going to see is that if I turn them on, in other words, I apply this high voltage, electrons go flying through the gas, you're going to see the colors. Okay? And first, let's start with the hydrogen lamp. So this is hydrogen here. Here we go. Okay, so you see it glowing. So now, if I can get the lights down, the reason that you have those glasses is if you look through them and look over to the side, look at the lamp. Let me blank my slide here. I don't know if my slide's in your way. Can you see it, or it has to go down further? I think we might. Do we need the lights down lower? Get the lights down lower? Okay, so do you see over to the side a series of lines? Okay, that's what we saw in the simulation, right? So your eye, what is your eye doing when you don't look through the glasses? It's averaging the light that's being emitted. What are we doing? The electrons are knocking, the moving electrons are knocking the electron up to a higher energy level, and as it relaxes down, you don't see every energy. Right? Does that make sense? We need a picture of you guys, because you guys look great with your white glasses on. All right. All right, now I'm going to move to the next one. What do you expect to see the same lines for a different atom? No, why not? Because the energy levels are at a different place. So that's helium. All right. Okay. So how many lines do you see? What do you see for helium? How many colors? Okay. Now this one is sodium. And by the way, if you live in San Jose, all of the street lights are sodium lamps, and they have a characteristic yellow color. All right. Now, this one, I know what you're seeing. I forgot to look at the helium one. You're seeing those two, or at least one, really bright yellow line, right? When I say line, I mean emission of light. It's a very narrow wavelength of yellow. Okay? All right, and here's the final one. The final one is mercury, which is in the fluorescent lights. So the fluorescent lights have mercury in them. And the way the fluorescent lights work is they have a white coating. And this emission from mercury makes that white coating glow. And one thing that you might notice is compared with incandescent lights, compared with the normal light bulb, this light was going to be much whiter from a fluorescent light, whereas from those light bulbs, they're much more yellow in color. Okay? Okay, so let's have the lights back up. Any questions on that? Does that make sense? So again, that emission that you're seeing, this is an emission of light, and the energy in was from electricity. So electrical energy in, light out, and did you see every color? No, only certain colors. Question? So that's a good question. Is it actually atoms in there or molecules? I believe that the energy going, there are H2 molecules in there, but it's a very low pressure gas. But I believe that once they're excited, they're probably atoms. There's so much energy going in here that it's enough to break the bond. So keep in mind that the energy of moving the electrons is very, very high. Okay? Other questions on this? Okay. All right, so now we want to take a look at this is what you saw. this is the emission spectrum. Remember, emission means light out. Okay, so light out. So we put energy in, we get light out. So energy is going in here. All right, light out. And then if you take that light through something that will spread it out, because your eye fools you, your eye just averages it, it collapses all the colors together. If you split it out, for hydrogen, you see this purple line, this blue line, and this red line. And again, what I mean by line is just a narrow wavelength that's getting emitted. So these are all discrete, we call it, or specific wavelengths of light. So it's only certain energies that get emitted. And you see here, it's shown, this is kind of what you saw over to the side. When you spread the light out, you see these bright wavelengths that come out, and only those wavelengths. Okay. All right, questions on that? So now what we want to do is take a look at models of the atom and try to make the connection between what we're seeing and the interaction with light and the models of the atom. And we're going to consider 5 different models, and I have, again, a nice simulation where you can start to take a look at what's going on. So these models, the first one is a billiard ball model. Okay? It's just that the atom is just a hard sphere. This is what Dalton thought. Now, I want to make sure that you understand what the evidence is that that's not what the atom looks like. The plum pudding model was one in which electrons were embedded in kind of a pudding that was, in quotes, some kind of a mass that had a positive charge on it. So there was positive charge distributed and electrons in there. The classical model, of course, which is a solar system model, has a problem, as you'll see. The electron ought to spiral into the nucleus, okay? What Bohr did, because it should be attracted, what Bohr did was to say, well, I'm going to just postulate that those electrons are in certain energy levels. All right? That's what he just suggested, that they would be in those energy levels. And then, of course, the quantum model has these kinds of orbitals. I'm shading them in different colors because they have a positive and negative sign on opposite sides of the node. There would be an s orbital. So there's all of these orbitals. So let's now take a look at how light might interact with these various models. Okay? So, all right. So what I have here is the billiard ball, and I have a light source that I can turn light on. And right now I'm going to start by shining white light on the billiard ball model of the atom. What do you expect might happen with the white light? So let's take a look. It's going to come across as different fuzzy photons. And what do you see all wavelengths doing? They're just reflected. So if we had a billiard ball model of the atom, would we have color? What would white light do if it hit a billiard ball model of the atom? It would all be reflected, right? Would red be absorbed? No. Look at what's happening. All are being reflected. So if atoms were billiard ball, you would not expect to see any color. Does that make sense? Okay. So now, let's stop the flow of electrons for a moment. Now we're going to go to the plum pudding model. And it's got a little blue dot in the middle for an electron. So as this light comes in, it might be able to interact with the electron, right? The question is, if this electron is just sitting in this positive charge, would it matter whether it was red light or blue light or yellow light? So again, let's watch. And you see that different energies come through and they move the electron, right? But if the electron could be anywhere in the atom, does it matter whether it's red light or blue light? What does the blue light do? It makes it move faster and farther, and what does the red light do? Lower energy. What is it? It moves it less. But my point is there any distinction between red, yellow, blue, right? They're all partially absorbed or reflected, right? They either go through or they're partially absorbed. So the world would kind of look gray, I would think. In other words, it wouldn't look bright white because it's not getting reflected. If all the atoms absorbed energy, the world would be black, dark. There would be no light. All the light would get absorbed. But here it's partially absorbed. Okay, questions on that before I go on? Okay, let me make sure that one thing I should add is that purple here is intended to be the ultraviolet. So in this simulation, the purple is the high energy light. Okay, so let's shut it off. Now I'm going to go to the classical solar system model. So if this electron really were attracted to a nucleus, what would it do? It ought to spiral in. So that's kind of the most weird thing of atoms of all. And so watch the way they show this. Okay, so let me just play that again. So they show it by, it really just ought to release a lot of energy as it collapses into the nucleus. So already we know there's something weird about atoms. Okay, so now we're going to move to Bohr's model or a shell model. So there's that electron for hydrogen in the 1s orbital. So I'm going to start by shining white light on it. What do you already know? Are all wavelengths of white light going to interact with that electron? No. Now you may think that the electron can move between energy levels and then fall back down, but why can't it do that? What's special about light? The photon has what? Very specific energy, and it can only transfer that energy. This is not like an electron. When the moving electron transfers its energy, it can slow down. Light can't slow down. It moves with the speed of light. So we can only transfer light of the right energy. So we can take a look at that. So here are the different ones, and you see what's happening. Every so often, it moves out. With certain colors, we'll move it out, and then what happens as it moves back in again. Okay, and we'll do this slowly with one at a time, but I hope what you see is that it can only move with certain colors of light to a certain energy level, and then it falls back down, and depending on where it falls to, it emits the light of only certain wavelengths. Does that make sense? So the Bohr model actually does explain why we have color. Okay? Because certain colors, in this case, are absorbed and only certain colors are emitted. Questions on that? We'll come back to this one in a moment. Now I also want to show you the quantum model, or Schrödinger's model. And what you see there, that little fuzzy sphere, is a 1s orbital. And now if you watch, as the light comes on, watch what happens. Okay, that was, those are high energy p orbitals, right? There's the 2p. 1, 2, that's the 4p. Oh, now, and you see how it's going to, depending on the energy of light, it goes to a p or s orbital of different energies. There it goes to a different p orbital. See the radial nodes in that p orbital, right? That's a p orbital of a higher n. That one's the 3p. That's the 2p. That's the another 3p in the other direction. 4p, I think. Okay? And then it emits as it goes back down. All right. So any questions on that? We're going to come back to this model in a moment. Okay. Okay. All right. So I think the main point that I want to make here is everything was reflected. So this one reflected all wavelengths. This one absorbed all wavelengths. And down here, this just doesn't work. It explodes. And these two, the main thing is that they absorb or emit, either way, only certain wavelengths. Okay? Okay, questions? Liza stopped asking questions. Okay. All right, so now what I want to show you here is I just want to help you keep track a little bit. You're going to have to start to organize this for yourself. Atomic absorption means the electron is excited, we call it, from the ground state. In other words, it's in the ground state, it's excited by light energy to a higher energy level. So in this, absorption means light in and the electron goes up. How does that light come back out again? What's a common way? Think about a black surface, you know, a black top, the street or whatever in the summer, right? The light's getting absorbed, the electrons are moving up, but when the electron goes back down again, how does the energy come back out again? Heat. Okay, so in this case, we have light in, and the predominant mode of getting it out is heat out. And I just want to emphasize again that this is only certain energies. So as long as the atom, and so this is the bound electron. In other words, the electron is just relocating on the atom only certain energies. Once you're above the ionization energy, then you can get all energies, as long as they're greater than the ionization energy. And that in this case, you have an unbound electron. And so, of course, the photon energy, we've already talked about this with the photoelectric effect, is just the ionization energy plus the kinetic energy. So that's absorption. What is emission? Atomic emission is when the light is emitted. And in that case, the electron is excited to a higher energy level with some other type of energy, and then light comes back out again. And so for thermal or electrical energy, and in other words, heat the atom really hot, like on the sun, or put electrical energy in, you get discrete or only certain wavelengths out. So discrete emission of light. And why did I put black body on this? Black body is also heated up and make it glow. But is that emission discrete? Remember what it looked like. So I just want to distinguish, when you have a lot of electrons around and a whole body, not an individual atom, you get a broad emission. Okay, so now we're going to take a look. What we just looked at was absorption and emission, and now I want to start with the absorption spectrum. So for hydrogen, this is just absorption now, not emission. All we're looking at now is shining light on it and looking at where that light is absorbed. So these are the places, okay, where light is absorbed. So at those energies, you see light absorption. And I want to go back to the simulation because we can actually show you how that works with this model. So I've got the Bohr model here, and now instead of using all kinds of light, white light, I'm going to use just certain energies of light. And what I'm going to start with right now is 122 nanometers of ultraviolet light. This is a very specific energy of light, and I'm going to start shining it. And what happens to the electron when I do that? Goes to what level? N equals 2. It's exactly N equals 2. Okay, and what's happening on the spectrometer? Do you see it's starting to count what? At 122 nanometers, what is it starting to see? Energy of light is hitting it, right? So the spectrometer down here is counting. That peak keeps getting bigger and bigger as the light comes on. All right, so that's n equals 1 to n equals 2. All right, now I want you to tell me what's going to happen when I go between n equals 2 and n equals 3. Okay? Remember light is special. So I'm going to go somewhere, let me see if I can move it, between n equals 2 and n equals 3. The energy, what's going to happen? For an electron, it's okay. But for light, is it okay? So what happens to that energy of light if I shine that energy of light on it? Does it get absorbed? What comes to your eye? Okay, so when you're shining light on the atom and the electron can go to a certain energy level, that energy goes away. It goes into the energy of moving the electron. But if there's no energy level, that light comes right through to your eye. So here's 111, all right? And you can watch all day and nothing's going to happen, all right? Because the electron can't take in energy between n equals 2 and n equals 3. It's a very special interaction between light and the electron. All right, now what happens if I go to the next energy level? Now I'm going to go to 104. This is nanometers. Okay, can't quite get there. I'm close. Now watch. So where did it go now? Goes to n equals 3. Now look at the spectrometer. Ooh, what did you just see there? Okay. So what's the spectrometer showing now? It's showing the photons that are emitted are coming from n equals 3 to n equals 2. Where is that one? What color is that one? Red. And what happens when it goes from n equals 3 all the way back down to n equals 1? So that's ultraviolet, and n equals 2 to n equals 1 is ultraviolet. So what we're seeing is the energies of the light that can be emitted in this case. Questions? Okay. All right, so these are good for you to play around with. They're available to you online, so you should take a look at this website because I think it really helps in understanding. So this is the spectrum that you would get in what I just showed you was the spectrum that we were getting. We were watching the emission of photons. This is the absorption of photons. And so what we see here is there's nothing in the visible. So if we just look at absorption for hydrogen, there's nothing in the visible. But in the ultraviolet, we actually see lots of absorption. And so what I want you to do now is these are the energy levels for a hydrogen atom over here. This is what this is. This is energy. And notice it's minus 1312. We remember that from photoelectron spectroscopy, 328, 146, 82. I want you to take a moment to figure out how is this number related to this graph. So tell me where that number is. Why is it 984? Why is that the energy of the light that's absorbed? So take a minute to discuss that so that you understand how to translate. Okay, so what's 984? How do you get that number? What's 984? Where does that number come from? No idea? Go ahead. Okay, so the electron is sitting down here for absorption. It's only in the lowest energy state. And so what you said was that that is the energy of light that's absorbed, which is the difference, right? So this is a delta energy, which is 984. Okay, so this is going from n equals 1 to 2. What is this next one? 1166. 1, 2, 3. And what's 1230? 1, 2, 4. Okay, so in each case here, for absorption, the electron is down in the lowest energy state, and the only absorptions that I see are these. Okay, so there are not so many absorptions. They're just from the lowest energy state to another level. What happens right here? It's right about 1312. What happens? Ionizes. So this is the ionization energy. And why is this black? Why are all wavelengths being absorbed once you're above the ionization energy? Because the electron just comes off with more kinetic energy, right? So it can have, once it's off the atom, it can have lots of different kinetic energies, but there's this very special thing that happens while it's on. So let me say again, these are the colors of light that would be absorbed, and what's happening in here? What's happening to the light that I'm shining of those energies? Goes right through. Okay? All right, so I want to make sure that in this case we were talking about absorption, meaning it's down in the lowest energy and the light is moving it up. So this is, I probably should say, light in, heat out. Okay, so now, this case, I'm going to do just the opposite. I am going to heat the atom to a very high temperature. So this is heat in, and now we're going to get light out. And I'm showing you two different pictures. I'm showing you the picture of the distance from the nucleus, and then over here is the energy level diagram for hydrogen. So, so what does the heat do? The heat puts a lot of energy in, and where does it move the electrons? Out, just like in the discharge tubes. And then what happens when the electrons move back down again? So the colors that you were seeing in the emission spectrum, the colors that you were seeing, the violet is the electron going from n equals 5, so this is 5, down to 2. This one, the blue-green line that you saw, was 4 down to 2. And the red line is 3 to 2. Okay? And going down to 1 is so far down, look at where 1 is, that the energy is in where? It's not in the visible anymore. Where is it? Ultraviolet. So the distinction I want to make here is on the last one, we could only go from n equals 1 to 2 to 3 to 4. But what's happening when we go down? We have many more emission lines, just like I already showed you, because you can emit in lots of different ways, okay? So remember, if you start from n equals 4, there are 6 energies that you see. Okay. And in fact, there are many, many. These are pretty complicated. So these are all the energies that can come out from hydrogen. So depending on whether they end up in n equals 1 or end up in n equals 2 or n equals 3, n equals 4, you get lots and lots of emission lines. In other words, lots of different colors, wavelengths of light are coming out. But I want to emphasize again, not all. Okay? The electron can't go between. So there's a whole space in here where there's no energy level or no place for the electron to be. It can only be at those specific energies. All right, so now I want you to take a look at this chem quiz. Oh, sorry, I'm out of order. Okay, these are just this is the energy level for hydrogen-like atom. If it's helium plus, what do you expect to happen to the energy levels and why? Is the n equal 1 level going to be at minus 1312? No, why not? More nucleus, okay? So in fact, the n equals 1 level is way down there for helium, okay? And there is this model for hydrogen-like atoms. So as long as there's only one electron, there's this simple energy relationship. So this is a constant here. This is the nuclear charge. This is the quantum number, the level it's in, and you can determine the energy. But only for hydrogen-like atoms. So that would be hydrogen, helium plus, lithium 2 plus. Once you have more electrons, obviously things change because the electrons can also repel each other. Okay, so I don't want to do this one. I want to do this one. So which energies can be absorbed by helium plus? Okay, so take a look at the energy level diagram that I just showed you and tell me which of these energies can be absorbed. Okay, finish up. I have a couple of quick demos I want to show you, so finish up. Okay, 5 more seconds. Okay, let's see how you did. Okay, so 5248 is enough to do what? Ionize. If you have more than the ionization energy, can you absorb it? Yes. And can you absorb 3,000? No. So in this case, you can actually do both of these. You can do, the correct answer here is E. Now, let me just end by saying that these spectra get very complicated. There's lots and lots of emission lines. Fireworks are no longer a mystery to you. Because this is all that they are, right? The colors, that was lithium. So in the fireworks, lithium is red. Here's calcium, orange. Sodium, what color is sodium? Yellow. Copper, Nice, huh? And the last one is potassium. And as you leave, you can watch my pickle. So I have a pickle here. And I'm going to put electrons through the pickle. And be sure you return the glasses when you leave. But here is the electrons through the pickle. Oh. Yeah. Oh, careful. Oh, there it goes. Kind of a different kind of light.